Okay, so welcome to this video on a past paper. This time we're doing the GCSE Physics higher tier paper, the first paper, so paper 1 of the November 21 exam series. So if there's anything in this paper which you guys would like me to go into in more detail, a separate video, please let me know. But other than that, let's get straight into it. So question 1, we've got an electric car being recharged. We've got a nice diagram there. And the charging station applies a direct potential difference across the battery of the car. What does direct potential difference mean? So this term we might not have come across before, direct potential difference, but one term we will have come across before is direct current, or DC. Now direct current, we should be very familiar with what that is. And if we were to look at it on a diagram, we could do a quick diagram in the corner here. You can put time and current over here, we'll put I for current. Direct current looks like this. And AC current, alternating current, looks like this. And so direct current, basically the difference is that the polarity doesn't change. So this side of the of our graph is positive and this side is negative. So you can see with direct current the polarity stays the same throughout the whole thing. With AC the polarity changes. So it's exactly the same thing with direct potential difference. If instead we change this, so we're not showing current anymore, we change this that now we are showing potential difference. So I'm going to write V, potential difference. Again, the top is positive, the bottom part of our chart is negative. Exactly the same thing. The direct voltage or the direct potential difference is going to have the same polarity the whole way through, whereas the alternating potential difference would have a alternating polarity. So that's what we mean when we say direct potential difference. It means the polarity, stays the same. And it's only 1 mark, so that should be enough to get your 1 mark. Okay, next part of the question, we've got which equation links energy transferred, power, and time. And so we should know that the equation for energy transferred, or the equation for power, is equal to energy transferred over time. And so if we rearrange that for energy transferred, we know that the energy transferred is equal to the power multiplied by the time. Okay, so it doesn't matter what form you know your equation in, as long as you can rearrange it like that. So now we can see energy transferred equals power multiplied by time. It's going to be that third option there. Okay, now a very common pattern, as we mentioned before, we've got in the first part, we're going to select the equation to use, and in the second part, we're going to be asked to actually use it. So in this time, in this second part, we've got the battery in the electric car can store 162 million joules of energy and has a power output of 7200 watts. I want to calculate the time taken to fully recharge the battery from 0. So because it's from 0, that means we need to go from 0 to 162 million. And so basically you need to transfer 162 million joules of energy, right? So we can use our equation, which we selected previously. The energy transferred is equal to the power multiplied by the time. What you'll notice though is that this time we're asked to find the time taken. So the time taken is on this side. We want to get that on its own, so we need to rearrange the equation. So the time taken is equal to the energy transferred over the power. Yeah. So again, doesn't matter what form we first knew our equation in, as long as you can rearrange for whatever actual quantity we need. So this time we need the time, so rearrange for the time. Now it's just a simple case of plugging in our numbers. So the time taken is equal to the energy transferred. And we know we need to transfer 162 million joules of energy and divide that through by the 7200 watts. And everything is in the units we'd expect in, so we don't need to do any conversions. So you plug that straight in, and when you do that into your calculator, you should get 22,500 seconds. Okay, so that's the second part of the question. Now, the next part of the question, we've got which equation links current, potential difference, and resistance. So you can see basically we've got the same pattern going on as a previous question. So let's select the correct equation, and then it should jump off the page to you, V equals IR. Yeah, that should be really familiar to you, Hooke's law. So you can say it's that one. Next part then, we're going to apply it. The potential difference across the battery is 480 volts. There's a current 15 amps in the circuit, connecting the battery to the motor of the electric circuit, or the electric car, and calculate the resistance of the motor. So let's write down our equation over here so we can see it all at once. V equals I multiplied by R. We want to find R, so we need to rearrange. So R equals V over I. And then again, it's just a simple case of plugging in our numbers. And again, everything is in the units we'd expect, so volts and amps. So we know our resistance is going to be given to us in the ohms that we want. So V is 480 volts. and divide that through by the 15 amps. And if you put that one into your calculator, you should get an answer of 32 ohms. Okay. Next part, different charging systems use different electrical currents. We've got charging system A has a current of 13 amps and B has a current of 26 amps. And both charging systems use a voltage of 230 volts. And we want to basically compare the time taken to recharge a battery using charging system A compared to charging system B. Okay, so first of all, in order to understand this question, we need to first relate both equations that we used previously. So we know that V equals IR, and we also know that the power is equal to the current multiplied by the voltage. So we can write this over here, power equals IV. And previously we used another equation for power, which was the energy transferred related to the power and the time. So we know that the energy transferred is equal to the power multiplied by the time. And so what we can do is we can plug in, basically replace P in both with the IV that we found in our first equation. So in this case, instead of writing P, we write I times V. So this gives us the energy transferred is equal to I times V times by time. So now we want to compare the time taken in order to charge the system. So what we'd be interested in is this form. So time taken is going to be equal to the energy transferred divided by I times V. So what we can say is that if V is the same and the energy transferred is the same, then depending on what we do to the current, that will change the time. So we know that the V is the same because they both use a voltage of 230 volts. And the energy transferred is going to be related to how much energy we need to recharge the battery. And because that's the same in both cases, that will also be constant. So what we're really trying to compare is the currents. So in system A, we've got a current of 13 amps. System B, we have a current of 26 amps. So in one of those, we've got basically twice the current. And you can see if we double the current, we're going to divide by basically a half. And if we're dividing by a half, that means over here we'd get half T. So when we double the current, we end up actually halving the time taken to transfer that same amount of energy. So which statement would be correct then? It would be this last statement here. The time taken using system A would be double the time of system B. Or in other words, the time taken in system B would be half the time in system A, since system B is the one which doubles the current. Yeah. So this is the one we tick. So hopefully that makes sense. Okay, great. Question 2 then. Energy from the sun is released by nuclear fusion. We want to complete the sentence. Nuclear fusion is a joined together of what? And during nuclear fusion, the total mass of the particles does what? So the first one is a joining together of nuclei, right? So you're going to collide together one nucleus from this side, one nucleus from this side, and you're going to join them together. And effectively, you're joining together several nucleus, so that's nuclei. During nuclear fusion, the total mass of the particles actually decreases. We know it decreases because we end up releasing energy, and energy and mass are related. And so if we end up releasing energy, then we need to also lose some mass. So that is decreases. 2.2, the nuclear fusion of deuterium is difficult to achieve on Earth because of the high temperature needed. Electricity is used to increase the temperature of 4 grams of deuterium by 50 million degrees Celsius, and we're given the specific heat capacity. So straight away, we're going to have to do something with this. Probably going to have to use this in our temperature equation. So calculate the energy needed to increase the temperature of deuterium by 50 million degrees Celsius. Great. So first of all, we want to write down the equation. So hopefully we're all familiar with the equation that the energy transferred is going to be equal to the mass multiplied by the specific heat capacity multiplied by the difference in temperature. Yeah. So we can identify all of these from the question. The difference in temperature is 5200. The specific capacity is 5200. The difference in temperature was 50 million. And the mass is given to us as 4 grams. So we should spot straight away that this is in grams. And for this equation, we need it in kilograms. So to convert 4 grams to kilograms, you should get that this is 4 times 10 to the minus 3 kilograms. Okay, so basically that's the equivalent. Okay, next we just want to plug in our numbers into our equation. So the energy is going to be equal to the mass. So we know it's 4 times 10 to the minus 3 multiplied by the specific heat capacity, which is given us to us as 5200, and multiplied by the difference in temperature, which is 50 million degrees Celsius. Okay, and when you put that all into your calculator, you should get an answer of 1 billion and 40 million in your calculator, or approximately 1.04 times 10 to the 9 joules. And that's exactly what we want to write in there. Okay, so that's that The next part then, the idea of obtaining power from nuclear fusion was investigated using models. The models were tested before starting to build the first commercial nuclear fusion power station. Suggest 2 reasons why models were tested. Well, it's a commercial nuclear fusion power station, so what's really important is that we want to make money from this, and we want to make sure that it works, first of all, yeah? So first of all, we want to test that fusion works. That would be valid for the first point. And the second point, we can say to actually understand the process that's going to be needed. So if you're going to do this on a commercial scale, you need to make sure that you know how to do fusion and you have all the processes in place to make sure you can keep doing fusion, so you can keep generating energy, and that way you're going to make sure you don't have any interruptions, anything like that. So these are just 2 examples you could put. It's a suggest question, so you shouldn't recognize this keyword. Suggest question, so really any reasonable suggestion that you make is gonna would be able to get you the marks, yeah? So you doesn't specifically have to be these 2. Just any reasonable thing should get you the mark, and you can check the mark scheme for all the accepted answers, and there's more than 2. Right, next part of the question then, we've got generating electricity using nuclear fusion will have fewer environmental effects than generating electricity using fossil fuels. And we want to explain one environmental effect of generating electricity using fossil fuels. Well, the first thing that you should really know about fossil fuels is that when you use them, they release CO2. Okay, so that's one environmental effect, but why is that a problem? Well, when you release CO2, this is what causes climate change. This causes climate change, or more specifically, it causes global warming. Okay, so that's what you put for your 2 marks. Remember, it's 2 marks in this case, so we need 2 different points. So this would be our first point, the fact that it releases CO2, and second point is the effect that this has. So you need both of them for the 2 marks. And that is question 2. Alright, so question 3 is an experimental question, and it is one experimental questions where students do tend to struggle, but actually, hopefully, this is going to be quite straightforward and we can do it together. So you've got a student investigating how the current in resistor R at constant temperature varied with a potential difference across a resistor, and they recorded both the positive and negative values of the current. And the figure 2 shows a circuit the student used. So you can see your resistor R, got a variable resistor over here, and we've got an ammeter and a voltmeter to measure the current and potential difference. So we want to describe a method that student A could use for this investigation, and this is a 6 marker. So I'm not going to write it down, but essentially with a 6 marker experimental question, you just need to go in a lot of detail, every step by step of what you do to basically what kind of instructions you'd give the student to conduct this investigation. So what you'd want to do is measure the current in R using the ammeter. So notice we say we measure the current, and we also say what we use to measure the current. So that would give you maybe a mark. Then you want to measure the potential difference across R using the voltmeter. So that's the first thing you do. You switch on your circuit, you take a reading for the current, take a reading for the voltmeter. Then how are we going to vary the resistance? Well, we vary the resistance of the whole circuit using the variable resistor. So we want to say we vary the resistance using the variable resistor, and we then can record a range of values of current and potential difference. So when we change this variable resistor, that's going to cause the current in our circuit to change, which is then going to have an effect on the voltmeter reading over here. So then you change the variable resistor and you take another reading of current and potential difference, and you repeat that process over again to get a range of values for both the current and potential difference. And you will get both positive and negative values. Okay, now to get the negative values, what you want to do, you want to reverse connection of R to the power supply. Yep, so remember we said over here we want to get both positive and negative values. So if this direction gives us positive values, then what we want to do is we want to actually switch these terminals. So basically this terminal connects over here, and we basically get this terminal over here. Yeah. And that would cause that would mean our current is flowing the other way, and so we'd get negative values of current, which is basically what we want. Another thing that you need to include in 6 markers is some precautions you might take. So essentially we want to keep this at a constant temperature. Yeah, so the clues are all in the question. We want to keep it at a constant temperature. What does that mean? Well, when we heat this resistor up too much, it's going to stop obeying Hooke's law. If we have too high values of voltage or current, that's going to cause this resistor to heat up. So we want to keep our current quite low to ensure that we avoid this big spike in temperature. So to do that, we can make sure we can switch off the circuit between the readings. So that way we're not unnecessarily running the circuit. We give the resistor a chance to cool down, dissipate any energy. We ensure we don't build up that temperature. And finally, then once we have that, what we want to do is plot a graph. So what you could say for 6 marks is you want to plot a graph of your current against your potential difference. And remember, because we've taken negative values of current, that graph also needs to go in the negative direction. So you can have something like this, right? So you wouldn't just look like this. We need to include the negative parts as well. And that's something you can say for 6 marks. You just need to go into enough detail and put a logical sequence of steps together for how the student would do this investigation. Okay, so that's the first part of the question. Second part, then, the student repeated the investigation, and during student B's investigation, the temperature of resistor R increased. So at first we had student A, and now student B is doing it again, but they found that their resistor actually, the temperature increased. So what effect would that have on the student B's results? So if the temperature of resistor R increased, what effect would that have on the results? Well, we should know, and I kind of alluded to it earlier, that generally with a resistor, it's going to obey Hooke's law, right? So we're going to see something like this. Hooke's law basically says that the current is directly proportional to the potential difference, okay? But what happens is that as we get to very high currents or very high potential differences, we will notice that this tends to bend away like this, okay? And what you notice is that at the top end, it stops obeying Hooke's law, and the temperature actually heats up when you get to very high currents. And as a result, what happens is the resistance actually increases. So because the resistance has now increased, it's no longer constant, so you don't get a constant gradient, and therefore we have a curve in our graph. So how would we write that then? Essentially, what you'd have is the fact that the current and the potential difference are not going to be directly proportional. And as a result, or this is because rather, the resistance of R increases. Okay, so that's what you say for your 2 marks. That's your first mark, that's your second mark. So hopefully that makes sense. The next part of the question then, we've got figure 3 showing a moving coil ammeter at one time in the investigation. What is the resolution of the moving coil ammeter? Well, we can see that we've got between 1 amp and 2 amps, we've got 1, 2, 3, 4 graduations. That means we've got 5 gaps, right? So we go 1 to 2 to 3 to 4 to 5. So therefore, the difference between 1 and 2 amps is 1 amp. Divided by the number of gaps is 5 jumps, if you like. So 1 over 5 is 0.2. So the resolution is 0.2 amps. Yeah. Next part of the question, student replace the moving coil ammeter with a digital ammeter, and figure 4 shows a reading of the digital ammeter. The digital ammeter has a higher resolution than the moving coil ammeter. Give one other reason why it would have been better to use a digital ammeter throughout this investigation. So one other thing is the digital ammeter is going to be much easier to read and less prone to error. The reason for that is no matter where you're looking from on the digital ammeter, let's say I'm looking from here, or I'm looking down here, or I'm looking from the right hand side, or down here, that's always going to say 1.34. It's very difficult to read that as anything other than 1.34. If instead we look back at our moving coil ammeter, if we look at it from a position above our desk, let's say we have the ammeter at our desk and we're standing up, then what might happen is this arrow, instead of looking like it's over here, it looks like it's over here, so we misread it. Whereas if we were looking from down here, then this arrow might look like it's all the way over here, so you might misread it. Obviously we're exaggerating, but essentially what this is called is parallax error, where because in analog instruments, the reading that you take is affected by where you take it from, your eyesight, what level your eyes are at. So you're meant to take it from eye level. So you're meant to bring your eye down here level with the instrument and take the reading like that. That's what we call parallax error if you take it from basically at an angle. Okay, so what we could write here, 1 mark, we could say, if we use a digital thermometer, we don't get parallax error. Yeah, so that's quite a good one. I've misspelled parallax. 1R parallax error. So that's what we call parallax error, is the one about the reading at an angle. Okay, and that's question 3. All done. Okay, question 4 then. A student investigated density of different fruits, and table 1 shows the results. So they worked out the density for several different fruits. So the student determined the volume of each fruit using a displacement can and a measuring cylinder. What other piece of equipment would the student need to determine the density of each fruit? So to answer this one, we need to know that density is related to the mass and the volume. So specifically, it's the mass per unit volume. So we also need the mass. We've already got the volume. He's measured that. So in order to measure the mass, then what piece of equipment do we actually need? Well, we can use a weighing scale, or set of weighing scales to work out the mass. Nice easy one to start off with. 4.2, write down the equation which links density, mass, and volume. And so essentially, the density, rho, is equal to the mass divided by the volume. Okay. And as expected, then we've written down the equation. Now we're going to be asked to apply it. So the mass of an apple is 85 grams. The density is 0.68 grams per centimeters cubed. We want to calculate the volume of the apple. And something quite key here is that we want to give our answer in centimeters cubed. So in this equation, generally the mass is kilograms and the volume is centimeters cubed. Sorry, the volume is meters cubed. And we tend to get an answer or density in the units of kilograms per meters cubed. Now in this case, because we want the answer in centimeters cubed, we don't need to convert anything because what we have is a mass in grams. We have the density in grams per centimeters cubed. And this is going to be equal to the mass in grams divided by the volume in centimeters cubed. Yeah, so you can kind of see where that comes from. Centimeters cubed is over here. The grams is over here. So we don't need to convert anything, quite helpfully, in our question. So we can just use the equation in the top part. So we know that the density is equal to the mass over the volume. So therefore, we want to rearrange for volume since that's what we're trying to find. The volume is going to be equal to the mass divided by the density. So the mass was 85 grams. And divide that through by the density of 0.68 grams per centimeters cubed. And if you put that into your calculator, you should get a volume of 125 centimeters cubed. Okay, so hopefully quite straightforward again. 4.4, the student only measured the volume of each fruit once. The volume measurement cannot be used to show that the method to measure volume gives precise readings. Give a reason why, or the reason why. Well, the definition of precise is where you take several readings and they end up being close together. Now, the problem we have is that we haven't taken several readings because we're told in the question we only took the reading once, right? Each fruit we measured it only once. So because there's no repeat readings, we can't say that it's precise. So we need repeat readings basically. Cool. And that's it for question 4. So let's move on to question 5. Okay, question 5, we were told that during 1 year, 1.25 times 10 to the 18 joules of energy is transferred from the national grid. And the number of seconds in 1 year is 3.16 times 10 to the 7. Calculate the mean energy transfer from the grid each second. So in order to answer this, basically you want to take the total energy transferred, which was 1.25 times 10 to the 18, divided by the number of seconds in the year, because we want the mean energy per second. So the number of seconds is actually given to us quite helpfully. So you just divide that through by 3.16 times 10 to the 7. So really easy question there. You just plug the numbers in, put that into your calculator, you get an answer which is 3.9556 and so on times 10 to the power of 10 joules. But what you're going to do is you're going to actually round this out to 3 significant figures. And so this is 3.96 times 10 to the 10 joules. Remember, this is the third significant figure. So you want to round this. And because this is 5, this rounds to 6. Yeah, so we just write here 3.96 times 10 to the 10. Cool. 5.2 then, we've got a house with a solar power system. The solar cells generate electricity. When the electricity generated by the solar cells is not needed, the energy is stored in a large battery. Cool. The charge flows through the cable between the solar cells and the battery in 24 hours was 27,000 coulombs. And we want to calculate the mean current in the cable. So to answer this question, we need to know the relationship between current and charge. And so we should know that current basically is the charge per second. So the charge, we're going to use a Q for charge per second. So we can write that as T for time, but remember this time has to be in seconds. So the charge is given to us as 27,000 coulombs. And the time is given to us as 24 hours, but remember we just said this needs to be in seconds. So because this needs to be in seconds, we need to convert this 24 hours to seconds. And so we know there's 60 minutes in every hour. and there's 60 seconds in every minute. So you just do 24 multiplied by 60 multiplied by 60 again, and you should get an answer of 86,400 seconds. Then you just can plug that straight into there. So this becomes 86,400, and then you can work out what that is, and you should get an answer of 0.3125 amps. Okay, you can write this over here. So again, hopefully quite straightforward. The only tricky bit here is just make sure you convert your hours. Right, 5.3, at one time the total power input to the solar cells was 7.8 kilowatts, and the efficiency of the solar cells was 0.15. Calculate the useful power output of the solar cells. So we just need to know the equation relating efficiency. So efficiency is going to be equal to the useful power out divided by the total power in. I'm actually given the efficiency and the total power, 7.8 and 0.15. And we want to calculate the useful power out. So we need to rearrange this equation. So efficiency multiplied by the total power is going to be equal to the useful power. And so we can just plug in our numbers now. Efficiency is 0.15 multiplied by the total power, 7.8 kilowatts. And so we should get an answer of 0.15 times 7.8. Should get 1.17 kilowatts. But remember, we want the answer in watts, so we need to multiply by 1000, and so our answer will be 1170 watts. Cool. Is unlikely now for the last part. It's unlikely that all of the electricity generated that the UK needs can be generated by solar power systems. Explain why. So what we have here is basically we want to use the information that we gathered in the previous parts of the question to answer this. So we just worked out that, well, one solar panel or one set of solar panels on a roof has a useful power output of 1170 watts. And we also know that the energy needed during 1 year, or that was transferred by the national grid in 1 year, was 1.25 times 10 to the 18 joules. So we can see here that if you were to imagine we convert this joules to watts, this is going to be quite a small amount of energy that's actually being transferred usefully. So what we'd say is that because there's a low useful power output of the solar cells, what you need is loads and loads of solar cells. Now, why is that a problem? Is that basically these solar cells need a really large area of land. So it's not impossible, but basically you need a lot of land in order to have enough solar cells to generate enough electricity to satisfy all of the UK's energy demands. Yeah, so that's 5.4, and hopefully that was fairly straightforward as well. Okay, so question 6 then, we've got figure 6 showing the mass number and the atomic number for the nuclei of 5 different atoms, and we're asked how many neutrons are there in a nucleus of atom A. So atom A, we can see, has a mass number of 234 and an atomic number of 86. Now, another word for the atomic number is the proton number. So this tells us the number of protons. And the mass number tells us the number of nucleons, which is the number of protons plus neutrons. Because each proton has a relative mass of 1, and each neutron also has a relative mass of 1. So the mass number is just both of those added together. So we can see for A, we have a mass number of 234, and that's going to be equal to the number of protons, which is given to us as 86, plus the number of neutrons. So then we just rearrange for the number of neutrons. It's going to be equal to 234 minus the 86, and if you put that into your calculator, you should get the number of neutrons as 148. So that's what we'll write here. Cool. Next part of the question: which two atoms in figure 6 are the same element? So the element, what decides an element is the atomic number. It's the number of protons. So you can see here for the atomic number 92, we've got both E and D, which have that same atomic number. They've got different masses, but the atomic number is what actually decides what an element is. So if both of those have an atomic number of 92, it's the same element. So we can write here D and D. Perfect. 6.3, nucleus B decays by emitting an alpha particle. Got alpha particle decay going on. We want to draw an arrow on figure 7 to represent the alpha decay. So with an alpha particle, in alpha decay, we emit an alpha particle, and an alpha particle is made up of 2 protons and 2 neutrons. So it has a mass number of 4 and an atomic number of 2, which means that basically our initial atom is going to decrease by a mass number of 4 and an atomic number of 2. So the mass number for B initially was 226, so that's going to come down to 222. And the atomic number was 88, so that's going to come down to 86. So we just need to draw a arrow going from there to this point, and that is the arrow that we drawn on like that. Cool. Next question. What is meant by the random nature of radioactive decay? Well, essentially, if it's random, it basically means that we can't predict which nucleus will decay next. So if you have a bunch of nuclei and it's all in a radioactive element, we don't know which of those nuclei is going to decay next. We know that they'll decay, but we don't know which one specifically. Next part, a polonium nucleus decays by emitting an alpha particle and forming a lead nucleus. Then you have beta particle decay going on to form bismuth, and the bismuth then decays again by beta particle decay to form polonium again. So we'll ask the question, explain how these three decays result in a nucleus of the original element polonium. So you can see we start off with polonium, we ended up with polonium. So to explain this one, we're going to look at each form of decay in turn, but we're going to specifically look at the atomic number. Remember, the atomic number is a proton number, and that decides what element we're dealing with. So we're only interested in that. So for the first one, we have alpha particle decay. So as you mentioned, alpha particle decay. Let's number these 1, 2, and 3. So remember, with the alpha particle decay, what happens to the atomic number is you lose 2 protons. Yeah, so you can say minus 2 protons. Because remember, we've released an alpha particle, and that consists of 2 protons and 2 neutrons. So that means 2 protons and 2 neutrons have been removed from our initial atom of polonium. And so we've lost 2 protons. Remember, we're only interested in the protons because we're only interested in the atomic number. For the second decay equation, we can see we have beta particle decay. Now, beta particle decay, we didn't cover yet, but basically, where in beta particle decay, you gain a proton and you lose a neutron, right? And again, the part that we're interested in is that we actually lose a proton. Sorry, it's the other way around. We lose a neutron and we gain a proton. So again, the part that we're interested in is the fact that we gain a proton. So we've got beta particle decay in the equation 2. So we gain 1 proton. And the last one is also beta particle decay. So we also gain another proton. Okay. So we can see for each of those, what's ended up happening is that we have the final atomic number, or the atomic number of the final atom is the same as the initial, or the atomic number that we started off with of the initial atom. Okay, so that should be enough to get the 3 marks. And that's it for question 6. Alright, question 7 then, we've got a student investigating how the current in a series circuit is varied with the resistance of a variable resistor. So that's the circuit she used, and this is the graph that they got. So you got resistance on the x-axis and the current in amps on the y-axis. So the resistance is the resistance of this variable resistor, and this is your current that you're measuring. Cool. So the question we're asked then is the battery had a power output of 230 milliwatts when the resistance of the variable resistor was 36 ohms. So determine the potential difference across the battery. Well, first of all, we're given this graph and we're given the resistance of the variable resistor, so we can work out the current. So if the resistance was 36 ohms, we can come over here, find 36. So you can see it's going up in 2, so 32, 34, 36. We can go up to the point where we get our 9. Then we come across and see the point where it hits on the y-axis. And you can see this is 0.08. Yes, these are going up in 1 amp. So this is 0.08 amps. You can write down here, the current is 0.08 amps. So now we have the current, we have the power, and we also have the resistance, 36 ohms, and we're trying to find the voltage. We want to find the potential difference. So what would the voltage be? Well, we've got current and we've got power. We know that the power is equal to the current multiplied by the voltage, and therefore the voltage, if we rearrange for that, would be equal to the power divided by the current. And then we just want to plug in our numbers. So we need to convert these 230 milliwatts into watts. So this would just be 230 times 10 to the minus 3 watts. And divide that by the current, which is 0.08 amps. And if you plug that into your calculator, you should get the final answer of 2.875 volts. And that's what you can write down there. There's a few different ways you can do that question, but that's just one example of how you could do it. The next question then, the student concluded the current in the circuit was inversely proportional to the resistance of the variable resistor. Explain how figure 9 shows that the student is correct. So first of all, the definition of something being proportional, whether it's inversely proportional or directly proportional. Well, if it's inversely proportional, we know that the current would be equal to the something K over the resistance R, where K basically is our constant, right? So we're saying that if something's inversely proportional, then it doesn't matter what K is exactly, but K is always going to be constant for any current and any resistance. So we can basically rearrange this to say that K is going to be equal to the current multiplied by the resistance. And if this is true, where we can use any current and any resistance, and we still get the same K, because remember K has to be constant, then we know that the relationship is inversely proportional. So to work that out, basically, we can come over here and select a few values to plug into our equation to test it, see if we get the same K. So for example, let's select something that's quite easy to read. Well, we've done one already, where we had 36 ohms. So 36 ohms was over here, and we read that off as having 0.08 amps. Remember? So we want to do 36 multiplied by 0.08. And if you calculate that, that should give you 2.88. Okay, so this doesn't have any units, it's just our constant, right? So this should be the same no matter what value of current and resistance we choose. So we're going to pick another one from our graph. So let's choose one that's quite easy to read. So let's use 40 ohms. So 40 ohms, again, we come across 40 ohms, we go to the line and we come across to the y-axis. You can see it's 0.06. So 40 multiplied by 0.06. Oh, sorry, it's 0.07, not 0.06. And if you put that into your calculator, you should get the same answer of 2.88. So you can see it's quite there. It is constant, and for good measure, we can just pick one more number to do. So let's do again one that's quite easy to read. Let's do 20. So you come up to 20, come across just there, and this gives us a value of 0.14. So we're going to do 20 multiplied by 0.14, and again you should get the answer of 2.88. Now we can see the K that we theorized is indeed constant, and therefore it is indeed inversely proportional. So that's what you'd show. You'd have to write this part for the first mark, and the second part mark would be for the examples. You need to give 3 different examples of pairs of values, and they work out to the same constant of 2.88. Alright, 7.3, figure 10 shows a circuit with a switch connected incorrectly, and explain how closing the switch would affect the current in the variable resistor. Well, if we close this switch, what would happen is the current has 2 different options to go, but one option is basically 0 resistance, and one option has some resistance of the variable resistor R. So you can see with the switch, basically we're theorizing that the switch has very low or 0 resistance, and this is what we call a short circuit. Essentially what we've done is we've said that the current doesn't have to go through all of this. It can take a much shorter route and can come through here and have basically experienced no resistance. As a result then, what would happen when we close the switch? What would happen to the current in the variable resistor? Well, the current basically be 0. And the reason for that is essentially we've created a short circuit. Cool. And that's it for question 7. Okay, next question, question 8. Figure 11 shows a toy car in different positions on a racing track. The toy car and the racing track can be modeled as a closed system. Why can the toy car and the racing track be considered a closed system? Well, we need to know the definition of a closed system, and it is basically one where the total energy of the system is going to remain constant. So in this case, because the total energy of the racing track and the car is constant, that means altogether the system, they are constant. It's a closed system. Cool. 8.2, the car is released from rest at position A and accelerates due to gravity down the track to position B. The mass of the car is 0.04, and the vertical height between A and B is 90, and the gravitational field strength is 9.8 newtons per kilogram. Calculate the maximum possible speed of the toy car when it reaches position B. So to do this, we want to work out our energy equations, and remember, because it's a closed system, that means the total energy at any point in time is always going to be the same. So we can work out the energy at A and compare it to the energy at B, and we know that the energy at A has to be equal to the energy at B, but there's going to be some energy transfers going on, so the types of energy might not be the same. So let's actually see this in practice. So at position A, what kinds of energy do we have? Well, it's at rest, so we know there's no kinetic energy. If something's not moving, there's no kinetic energy. But we do know that it was raised 90 centimeters above B. So we know there's going to be some gravitational potential energy. So we can say that here, there's going to be gravitational potential energy. Now let's look at position B. So at position B, the car is moving, so there's going to be some kinetic energy. Is there going to be any gravitational potential energy? Well, because we said A is 90 centimeters above B, we can basically say that B is at 0 centimeters, and so there's going to be no gravitational potential energy because it's not raised at any height. So we've just got kinetic energy. And remember our definition in the earlier part, because it's a closed system, we know that the gravitational potential energy, therefore, is going to be equal to the kinetic energy. Great. So now we can start to plug some of our numbers in. So the equation for gravitational potential energy we should know is mass times gravitational potential or gravitational field strength, multiplied by the height. And the equation for kinetic energy is a half times the mass multiplied by the velocity squared. So let's do the gravitational potential energy at A first. So that's the mass, which is given to us as 0.04 kilograms, multiplied by the gravitational field strength given to us as 9.8 newtons per kilogram, multiplied by the height, which is given to us as 90 centimeters, and we're going to convert that to meters because we need everything to be in the standard form. So this is going to become 0.9 meters. And if you put that into our calculator, we should get an answer of 0.3528 joules. Cool. Now we can compare this to the kinetic energy. So the kinetic energy is going to be equal to half times the mass times velocity squared. So half of the mass is 0.02 kilograms. And this is going to be multiplied by velocity squared. And remember, because these are equal to each other, we can say that this is equal to 0.3528 joules. So now it's just a case we want to find out the maximum possible speed. So we want to work out what V is. So we can rearrange for V. So V is going to be equal to 0.3528 all divided by 0.02. And we're going to have to square root it because this would be V squared. So if we square root that, and we can just plug that into our equation, plug that into our calculator, and we should get an answer of 4.2 meters per second. Okay. So that would be a maximum speed. We're saying that all of the gravitational potential energy that we started off with was converted to kinetic energy, and none of the energy was lost, and therefore the maximum possible speed is 4.2 meters per second. Okay, so that's 5 marks, but hopefully you can understand each stage, and it's quite straightforward to go from each step to the next. Okay, next question then. At position C, the car's gravitational potential energy is 0.02 joules greater than at position B. So this is position B, and position C is right at the top of the loop. How much kinetic energy does the car need at position B to complete the loop of the track? So essentially, it means that from B to C, we have to gain 0.2 joules of energy. So if you want to complete the actual loop and want the car to come down from C and complete the loop, then how much energy do we need? Well, the idea is that we're going to need slightly more than 0.2 joules. And the reason for that is that if we have 0.2 joules at B, that means that by the time we get to C, we've used all our 0.2 joules of kinetic energy and we've converted it to gravitational potential energy. So at C, our kinetic energy is going to be 0. If our kinetic energy is 0 at C, that means the car is going to stop moving and it's going to fall down. What we need is the car to keep moving, and so we need some kinetic energy. So we need at least a little bit of kinetic energy, and so we need more than 0.2 joules. So the reason we can say is that we need car needs to be moving. Cool, and that is that. So let's move on to the next question. Okay, question 9, we've got an experimental setup again, and we've got a teacher demonstrating the relationship between the pressure in a gas and the volume of the gas. So there's the equipment used, and these are steps they took. So they record an initial volume of gas in the syringe and the pressure reading before any weights are attached. They attached a 2 Newton weight to the syringe, then recorded the volume of the gas and the reading on the pressure gauge, and they repeated steps 2 and 3 until a weight of 12 newtons is attached to the syringe. So what was the range of force used? Well, we can see in step 1 we had 0 newtons of force being used, and in step 4 we've got 12 newtons of force. So it goes all the way up to 12 newtons. So the range is going to be from 0 newtons to 12 newtons. Give one control variable. Well, one control variable is one thing that we kept the same. So although we didn't keep the volume of gas in the syringe the same because that's changing, we did keep the amount of gas, if you like. So the amount of gas, or more precisely, the mass of the gas. Okay, so that was the same throughout the experiment. 9.3, when the volume of gas in the cylinder was 45 centimeters cubed, the pressure gauge showed a value of 60 kilopascals. Calculate the pressure in the gas when the volume of the gas was 40 centimeters cubed. Well, we should know the relationship between volume and pressure, and the volume multiplied by the pressure is going to give a constant. Okay, so we're given two values for volume and pressure. So 45 multiplied by 60 should give us our constant 2700. Now the idea is that any value or any pairs of values for volume and pressure, no matter what they are, should still give this constant 2700. So in this case, we're asked to work out what the pressure is when our volume is 40 centimeters cubed. So we can say that 40 multiplied by some pressure we don't know, we're going to work that out, is still going to be equal to the same constant 2700. Okay, so then it's just a case of rearranging for the pressure. So the pressure is equal to 2700 divided by the volume of 40 centimeters cubed. And remember, the reason we can do this is because the units here are the same, which means the units that we work out for the pressure is also going to be the same. So this is going to be given to us in kilopascals. So 2700 divided by 40, if you put that one into your calculator, you should get an answer of 67.5 kilopascals. Cool. Next part, when the volume of the gas in the syringe is increased, the pressure on the inside of the syringe is decreased. Explain why. Well, how does pressure actually work? What is actually going on? Well, if there's pressure between the particles of gas and the inside of the ball, that basically means that there's collisions between the particles and the inside of the ball. So when we increase the volume of the gas, what we're saying is there's less frequent collisions between the particles and the wall. Remember, because we're looking at the pressure of the on the inside of the wall, we need to look at what's hitting the inside of the wall. That's the particles and the wall. So we increase the volume, the particles are much more spread apart, and we're going to get less frequent collisions between the particles themselves and between the particles and the wall. That means that if there's less frequent collisions, what that means is that there's less average force on the wall. So if you imagine if we were to work out the force at any point in time, we could kind of work out the average force, and it's not going to be constant because remember the collisions are random, but we can kind of average out to get the average force. So if there's less average force, what that means is that there's less pressure, because force, or rather pressure, is equal to force over area. Yeah, so pressure is the force per unit area. So if we're saying there's less average force, then that means that the pressure is going to be lower. Okay, so that's what you say for your 3 marks. And that's it for question 9. So let's move on to question 10. Okay, question 10, I think the penultimate question in this exam paper. Figure 13 shows some overhead power cables in the national grid. Explain the advantage of transmitting electricity at a very high potential difference. So this is quite a standard question, and we should have a standard answer ready for it. So the reason why we transport things at a high potential difference is actually to do with the current. It may seem kind of a bit of a trick question. It's asking about the potential difference, but the reason is that if you've got a high potential difference, that means you've got a very low current. If you have a very low current, that means we generate a lot less heat, right? So we lose a lot less heat energy, lose a lot less electrical energy as heat energy through the cables. As you imagine, if we're transporting it through here, if we're generating loads and loads of heat, this is just going to be dissipated away into the air. So we're just going to end up heating up our cables and heating up the air around it. And that's not useful energy. So as you can imagine, if we're able to decrease the amount of heat energy that we lose, that will increase our efficiency. Yeah, because we'd have more useful energy being transferred to the point where we actually need to use it, right? Because we lost less heat. So that's the 3 marks. 10.2 is dangerous for a person to fly a kite near an overhead power cable. Figure 14 shows a person flying a kite. The person could receive a fatal electrical shock if the kite was very close to but not touching the power cable. So explain why. So essentially, what I asked is, if you've got a power cable above this kid here over here, and it's not touching it, but how could they still get an electric shock? Well, what happens is, remember, we're working at very high voltages through our cable. As a result, we might end up with an electric field, which is a very high electric field strength, and that means that the air around it can actually become ionized. So how that works is you might have air made up of different particles, and the particles might have some positive parts, some negative parts, negative parts, but overall the air itself is not a conductor or very good conductor, because most of these, the overall charge is going to be 0. Yeah, you can see they've all got negative and positive parts. The overall charge is 0. However, when you have a very high electric field in the presence of the air, what can happen is some of these negative particles or some of these positive particles might be attracted to the field, and you end up losing the molecule ends up losing some of its constituent atoms. And what can happen is then you're left with an overall negative particle. So you can end up with an overall negative particle or overall charged particles. And what that means is that we've got ions, and you might know from chemistry, when you have ions, they are actually quite good conductors of charge. So you end up with ions being able to transfer the charge between the electric field into the kite through the string and end up electrocuting the kid. Yeah, so that's what you basically say for 3 marks. You have a very high electric field strength that can cause ionization of the air around it, and that means that the air basically can conduct it. So conduct through the string into the kid, and that's it. Cool. Next part of the question then: if scientists investigated how the potential difference needed for air to conduct charge varies with the distance between a cable and the earth. So we've got figure 15 showing the results of that, and the data in figure 15 gives a relationship between potential difference and the distance when the air is dry. When the humidity of air increases, the air becomes a better conductor of electricity. So this phrase, a better conductor of electricity, what does it actually mean? Well, essentially it just means that we have a lower resistance. Yeah, things with a lower resistance tends to be better conductors of electricity. When you have things with a very high resistance, that's what we kind of term, oh, these are insulators, right? They're not good conductors. So you want to draw a line on figure 15 to show how the potential difference changes with the distance of if the humidity of the air increases. Well, we just said if the humidity is increased, the air becomes a better conductor. So what we'd expect is that the potential difference needed for it to conduct would actually be a lot lower. So for every distance here, we can see that it would be the potential difference would be lower. But the key thing is that it has to still pass through 0, 0. The reason for that is if you have a distance of 0 meters, then you don't need any potential, well, you wouldn't have a potential difference basically, because the charge would just go straight through. You wouldn't have an opportunity to build up any potential difference. And so it still needs to go through the origin 0, 0, but you can see the line would be lower than the black line at the top that was originally drawn. So that would be that for 2 marks. Okay, so the last part of this question then, we've got figure 16 showing a cross-section through a power cable. And we can see it's made up of both steel and aluminium wires. And we're told that the aluminium wire is a better conductor than the steel wire. And the individual wires behave as if they are resistors connected in parallel. Explain why the current in the steel wire is different to the current in a single aluminium wire. So the fact is that we're saying that we have a single power cable and it's connected from the same source. So the potential difference will be the same across the cable, but inside of the cable we've got steel and aluminium. So was told that the current is different, and the reason for that is the steel and the aluminium, even though they have the same potential difference across them because they're connected to the same source, the fact is that they're different materials, so they have different resistivity. So the resistance of the steel and the aluminium are going to be different. Okay, so because they have different resistance, that means they're going to end up with the different currents. And the second one will basically say even though the potential difference is the same. Final part of that question. So let's move on to question 11. Okay, final question of this paper then. We have a student investigating how the temperature of a lump of ice varied as the ice was heated. Student recorded the temperature until the ice melted and the water produced boiled. And figure 17 shows the student's results, and the power output of the heater was constant. The first question then, the specific heat capacity of ice is less than the specific heat capacity of water, and explain how figure 17 shows this. So essentially we can see we've got 2 different sections here. So as the temperature is 0 degrees, this is no longer going to be, well, it's going to melt. So anything above here is going to be when the ice is turned into water, and anything above 100 is when the ice is turned into a gas. So the straight lines are where it's vaporizing, or this is the latent heat of vaporization and the latent heat of fusion, which we'll get into later. But for this first part, we just need to explain why the figure shows that the specific heat capacity of ice is less than that of water, and that's to do with the gradient over here. So the gradient is basically showing us the difference in temperature over the difference in time, but essentially we can think of this difference in time as a difference in energy, and the reason for that is because the power output was constant. And that means that because the power output is constant, then across any period of time, that means we're going to have the same amount of energy. So basically the time is telling us how much energy we've transferred to our ice or water in this case. So then we can look at the formula for the specific heat capacity, and that might know it in this form where E equals mc delta T, and we rearrange for specific heat capacity C, that is equal to E over m delta T. And essentially the m is constant, so what we can say is that the C is proportional to E over delta T, which looks very similar to our gradient over here, but you can see it's just basically the reciprocal. So what we'd say is that the specific capacity is proportional or inversely proportional to E over delta T, or is proportional to 1 over the gradient. Okay, so what that is telling us is that the larger this gradient is, the lower our specific heat capacity is. So that means if the line is steeper, our specific heat capacity is lower. So that's exactly what we'd say, is that because we have a steeper line, that means we have a lower specific heat capacity. And the steeper line is for ice than water. Okay, and so that should give you your 2 marks. And this part over here where we've basically rearranged and found the gradient is just to explain it, but that's all you'd have to write for 2 marks. Now, the second part of the question, the specific latent heat of fusion of ice is less than the specific latent heat of vaporization of water. Explain how figure 17 shows this. So this is where we mentioned, so we need to identify, first of all, this is the latent heat of fusion of ice. Okay, so this is where the temperature stays constant as the ice changes state to water. So that energy is still being supplied. Where does that energy go? Well, that's the latent heat of fusion. And then over here, we've got the latent heat of vaporization. So again, the temperature stays constant despite the fact that we're supplying energy. And the energy goes into changing the state of the water to a gas when it vaporizes and boils. Okay, so that's and so then which one is larger? Well, we can see, as we mentioned before, the time taken basically tells us how much energy we've put in. So therefore, because the time taken for the latent heat of vaporization is a lot larger than that for fusion, that means that it is the vaporization which is larger. So what we'd say for the 2 marks is the water took more time to vaporize than ice took to melt, and so therefore you need less energy. Okay, less energy of fusion, or less energy to change the state from solid to liquid. A second student did the same investigation and recorded the temperature until the water produced boiled. In the second student's investigation, more thermal energy was transferred to the surroundings. Describe 2 ways the results of the experiment in figure 17 would have been different. Well, if you're transferring more energy to the surroundings, that means that less energy is actually being supplied to your ice or your water. So what you'd have is that your gradients would be less steep, and your time taken for the ice to melt or the water to boil would also be a lot longer, because you're transferring less energy directly to the ice or the water, and more of it is being lost. But even though the same input, you still have the same input energy, if you like. So what we could say for 2 marks is that the ice or the water would take longer to increase the temp, and it would also take longer to change state. Okay, so that's 11.3, and the final question then, it is the final question. Its calculation is, we've got, when the water was boiling, we have 0.03 kilos of water turning into steam, and the energy transferred was 69 kilojoules. Calculate the specific latent heat of vaporization of water, and it is 5 marks. So let's go through this one step by step. So first of all, we need to know the formula for the specific latent heat of vaporization, or specific latent heat in general. The energy transferred is equal to the specific latent heat, which we'll call this, multiplied by, or we'll just call it L, latent heat, multiplied by the mass. Okay, so we're given the energy transferred, and we're given the mass, so we can work out the latent heat. So the energy was 69 kilojoules, so we'll convert this into joules just to have everything in the standard units. So 69,000 joules, or rather 69,000 joules is equal to L multiplied by M. So 69,000 divided by M of 0.03 kilograms will give us the specific latent heat L, which gives us 2,300,000. So this is so that's how we work it out basically, and we can even say that this is 2.3 times 10 to the 6. And what would the units be? Well, we've got joules over here, so 669,000 joules, and we've got kilograms down here. So this would be joules per kilogram. Okay, so if you were to keep this as kilojoules, you could do, and you would just get the answer in kilojoules per kilogram. That's the only difference. Okay, so that's 5 marks, and actually you can see it's not particularly advanced. We just will need this equation. Then the rest of it is just a case of plugging our numbers in, rearranging the equation successfully, and then working out what our units would be. Okay, so not actually that tricky for an end of paper question, hopefully. So yeah, so the answer we could put 2.3 times 10 to the 6 joules per kilogram. Okay, so that's the end of the paper. Hopefully that was useful. If there was anything in this paper which you would like to go through in more detail, please leave a comment. Please leave a like if you found it useful, and do drop a subscribe. Thank you, and see you in the next one.